Present, sir.
right? Samir Ahmad,
Present, sir.
right? Sania,
Present, sir.
okay. Sanjay, Sanjay, Sankalp,
Present, sir.
right? Sanket,
Yes, sir.
okay. Shiraj, Shiraj, Shivnanda, Shivnanda, Shraddha,
Present, sir.
okay. Shubham,
Present, sir.
right? Sumit, Sumit, Suraya Banu,
Present, sir.
right? Tejas, Tejas, Vivek, Vivek, Yamunappa, Yamunappa, गांवकर रजत रामचंद्र, गांवकर रजत रामचंद्र, मंजुनाथ, मंजुनाथ, प्रथमेश, प्रथमेश, प्रथमेश पाटिल, जोसलिनो, जोसलिनो, anybody else present? Tejas I have marked, Shiraj Mujawar I have marked. Anybody else? Okay. Let us begin with the today's session. In yesterday's class, we discussed about the collector feedback bias circuit, or it is also called as collector to base bias circuit or biasing with voltage feedback circuit. Okay.
Sir.
These are various names for the collector to base bias circuit.
Sir.
Right? Yes.
Present, sir. Prathamesh Patil.
Okay. Right. So we are discussing about the collector feedback, collector to base bias circuit or collector feedback bias circuit. Then we had analyzed the DC analysis. We had done the DC analysis of the circuit. Okay, then we got various equations. We got the equation for IC as VCC minus VB divided by RC plus RE. Okay, then expression for VCE, it is VC is equal to VCC minus IC into RC plus RE, that equation. Then saturation condition for the transistor for the collector to base bias circuit, it is same with IC saturation is equal to VCC divided by RC plus RE as that of the emitter bias and voltage divider bias circuits. Then later we discussed S of ICO for collector feedback bias circuit, S of ICO for collector feedback bias circuit. Okay, here the general equation is S of ICO is 1 plus beta divided by 1 minus beta dou IB by dou IC. Using this equation, we derived the equation for the S of ICO, that is beta plus 1 into 1 plus RB divided by RC plus RE, the whole divided by 1 plus beta plus RB by RC plus RE. Okay, so this was the yesterday's discussion. In continuation with that, today we will be discussing with the S of VBE, S of VBE and S of beta. Okay, we know that S of VB is dou IC by dou VBE, that is change in collector current with respect to base to emitter voltage. Let us consider equation 2 here. Equation 2 is the equation that we had used for the input portion of the collector feedback bias circuit, that is this circuit. Okay, that is VCC is equal to RC plus RE into IC plus RC plus RE plus RB into IB plus VBE. The basic equation is VCC is IC RC plus IB RC. IC, this is the basic equation. We got this from this equation basically. That is VCC is IC plus IB into RC plus IB RB plus VBE plus IERA. This is the equation that we are applying for the input loop, for the input portion. As we apply this, then we are substituting IE as IB plus IC. When you substitute IB plus IC for IE, then we get the equation VCC is equal to RC plus RE into IC plus RC plus RE plus RB into IB plus VBE. Okay, this equation we are making use of here. The same equation VCC is equal to RC plus RE into IC plus RC plus RE plus RB into IB plus VBE. Right now, in this equation, IC is beta times IB. We know that IC is equal to beta into IB, or IB is IC by beta. IC is equal to beta into IB, or IB is equal to IC by beta. Therefore, VCC will be RC plus RE into IC plus REC plus RE plus RB. IB we are substituting as IC by beta. Therefore, this is replaced by IC by beta plus VBE plus VBE. Take it as equation 4. Next, here this equation we have to differentiate partially now. So differentiating partially with respect to IC, keeping beta constant. If you want to find out S of VB, that is dou IC by dou VB, you have to differentiate with respect to IC, keeping the other parameter constant, that is keeping beta constant, so that we get in the form of dou VBE by dou IC, or in the form of dou IC by dou VBE. That is nothing but our S of VBE. When we differentiate this equation with respect to IC, differentiation of VCC, it is the constant, it is 0. That is equal to RC plus RE. Differentiation of IC is 1. So that is 0 is equal to RC plus RE plus RC plus RE plus RB by beta. Differentiation of IC is 1. So RC plus RE plus RB by beta. Okay, plus differentiation of VBE, that will be dou VBE by dou IC. Dou VBE by dou IC. It is dou VBE by dou IC. What we got here, differentiation of VCC is 0, RC plus RE, differentiation of IC is 1, so it is RC plus RE plus RC plus RE plus RB by beta, these are all constant. Differentiation of IC with respect to IC is 1, okay, so it is RC plus RE plus RB by beta plus differentiation of VB is dou VBE by dou IC, dou VBE by dou IC. Simplify further, 0 is equal to, take this beta, beta is the LCM here, okay, so beta is the LCM for RC plus RE and the second term. Now beta will come and it gets multiplied here with RC plus RE as it is the LCM. Therefore, we get beta into RC plus RE plus RC plus RE plus RB, that divided by beta plus dou VBE by dou IC, dou VBE by dou IC. Now we want equation for dou VBE by dou IC. Therefore, dou VBE by dou IC is equal to this portion, whatever is there, if you take it to the LHS, it will become minus, because it is plus here. If you take it to the LHS, it will become minus of beta into RC plus RE plus RC plus RE plus RB, the whole divided by beta. Okay, we got the equation for dou VBE by dou IC. Now what is our S of VBE? It is dou IC by dou VBE. Now the obtained equation is dou VBE by dou IC, but we want it in the form of dou IC by dou VBE. So what we have to do here, we have to rearrange this equation in the form of dou IC by dou VBE. So this dou IC, if you take it to the numerator, it will come here, dou IC. And if you dou VB, if you take it to RHS, it will come to the denominator. So we get dou IC by dou VB is equal to, similarly, this beta, if you take it to the LHS, it will come to the numerator, and this term, okay, the numerator term, that is minus of beta into RC plus RE plus RC plus RE plus RB, if we take it to the LHS, it will come to the denominator. Okay, so we get finally dou IC by dou VB is equal to minus beta, the whole divided by this term will come to the denominator, that is beta into RC plus RE plus RC plus RE plus RB. What is dou IC by dou VBE? It is S of VBE. Therefore, S of VBE will be equal to minus beta, that divided by beta. See here, RC plus RE is common. Take it outside. If you take RC plus RE common, it will be beta plus 1 plus RB. Is it not? If you take RC plus RE common here, right? RC plus RE is common. So RC plus RE, if you take common, so it will be beta inside the bracket beta plus 1, then other term will be plus RB. Okay, this is the final equation for S of VBE. Therefore, what we got, S of VBE as minus beta, the divided by beta plus 1, because RC plus RE is common, so it will be beta plus 1 plus RB. That is, S of VBE is minus beta, the whole divided by beta plus 1 into RC plus RE plus RB. Okay, so this is the equation for stability factor S of VBE. Again, to derive this S of VB, we are considering the input path or the input portion of the collector feedback bias circuit. Okay, whenever you are deriving the S of VB, we are considering the input portion of the collector to, whenever you are deriving S of VB for the collector feedback bias circuit, we are considering the input portion of the collector to feedback bias circuit here. Okay. The next is stability factor S of beta. Stability factor S of beta. This portion is understood here. S of VB, is it clear? S of VB, is it clear? How to derive stability factor S of VBE? Yes, is it understood here? S of VBE. Is it clear here? How to derive S of VBE? Understood? Joshi? Abhay? Abhay? Chandrasekhar?
Yes, sir.
Understood?
Yes, sir.
Okay. Okay. Rutik Chopde? Rutik?
Yes, sir. Understood, sir.
Understood. Okay. Sankalp? Sankalp? Shraddha? Shraddha? Is it clear here? Shraddha? Shubham? Shubham?
Yes, sir.
Understood? S of VB, how to derive it?
Yes, sir.
Okay. Pratmesh? Pratmesh? Patil? Pratmesh Patil? Tejas? 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 Surya Banu?
Yes, sir.
Understood this derivation?
Yes, sir.
Any doubts here in this derivation?
No, sir.
Any problem in understanding?
No, sir.
Okay. Fine. So let us move on to the next derivation, that is S of beta. So S of beta is given by the equation delta IC by delta beta, as we are deriving for the S of beta for the other biasing circuits, right? What we have done there, whenever we want to derive S of beta, we are not differentiating partially because it is more time consuming. Okay, equations are little complex as compared to this method of finding the S of beta. Therefore, the method that we are following is we are finding the S of beta as delta IC by delta beta. From equation 4, again this is the equation 4 is the input path equation. Okay, whatever we have got from the previous. Okay, but in examination, if they ask only this S of beta, you have to take the input portion equation and you have to get it in this form, right? You have to get it in this form by considering the input portion equation, right? But if they ask all the three, if they ask all the three, that is S of ICO, S of EB, S of beta, then you can take from the previous. If you are deriving S of beta, you can take from the previous, just from S of VB, this equation 4, and you can directly use it. But if they are asking only particularly S of beta in the examination, then what you have to do, you have to apply the KVL equation to the input portion of the collector feedback bias circuit, right? And then substitute IA as IB plus IC. Okay, then IB as IC by beta, and then get it in this form. Okay, get it in this form. That is VCC is equal to RC plus RE into IC plus RC plus RE plus RB into IC by beta plus VBE. Let us see what is equation 4 in the previous one. Equation 4 is this equation here. That is what we got by substituting IB as IC by beta, that equation. Okay, this equation here, equation number 4. The same equation we will be considering here for derivation of S of beta. That is VCC is equal to RC plus RE into IC plus RC plus RE plus RB into IC by beta plus VBE. Expand this, that is VCC will be equal to RC IC plus RE IC plus RC IC by beta plus RE into IC by beta plus RB into IC by beta plus VBE plus VBE. Okay, This is the equation that we get after expanding the previous equation. Now VB, let us take it to the LHS, it will be minus VB. If we take plus VB to the LHS, it will be minus VB. Therefore, VCC minus VB is equal to RC IC plus RE into IC. This is RC means is collector resistance into collector current plus emitter resistance into collector current. IC is collector current. Okay. Plus these are all, beta is common in all these three. So take beta here as a common factor. So we get RCIC plus RE into IC plus RB into IC, that divided by beta. Now VCC minus VBE is equal to, if we take beta LCM, so this beta gets multiplied here to this part of this term of the equation. Therefore you get RCIC plus RE into IC, that multiplied by beta plus this term RCIC plus RE into IC plus RB into IC, the whole divided by beta. Now beta, let us multiply it to the LHS here. So if you take it to the LHS, it gets multiplied with this VCC minus VBE. That is VCC minus VBE into beta. This is equal to RC into IC into beta plus RE into IC into beta plus RCIC plus RE into IC plus RB into IC. That is VCC minus VBE into beta. So now which is common term here? IC is common. You can see here IC is there in this term. It is in there in this. It is there in this. It is there in almost all the terms. In all the terms IC is existing. Therefore take IC common, collector current. That multiplied by RC beta plus RE beta plus RC plus RE plus RB. Okay. So we got this equation. Okay. By taking collector current IC common factor. Now we want the equation for IC. Okay. Because what is the equation for S of beta here? Delta IC by delta beta. Therefore get the equation for the collector current. The method remains the same with whether you are finding S of beta for fixed bias circuit or for emitter bias circuit or for voltage divider bias circuit or for collector feedback bias circuit. The method, the approach for finding S of beta is the same, whichever biasing method you are using. Okay. So you get IC as IC. If you want, you have to rearrange the equation. If you rearrange it, you will get IC is equal to VCC minus VB into beta. This will be as it is. So this multiplied term here, product term, this will come to a denominator. So we get IC is equal to VCC minus VB into beta, that divided by RC beta plus RE into beta plus RC plus RE plus RB. That is IC is equal to VCC minus VB into beta, the whole divided by, again RC beta it is plus RE beta. Beta is common factor. Take it out. You get beta into RC plus RE plus RC plus RE plus RB. Okay. That is IC will be equal to VCC minus VB into beta, the whole divided by RC plus RE is common. RC plus RE is common. If you take RC plus RE as common, it will be RC plus RE into beta plus 1. RC plus RE is common factor. So that is multiplied by beta plus 1 plus RB plus RB. Take it as equation 6. This is a simplified equation for the collector current. Here we have to make certain assumptions. You all know what assumptions we have to make. Okay, what are the assumptions that we have to make here? 2 assumptions for finding the equation for S of beta. What assumptions we need to make here? Is anybody? What assumptions we are required to make here? Janvi? Janvi? Mahadev? 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 Mohammed? Mohammed?
Yes, sir. Yes, sir.
What assumptions we are required to make here?
The temperature.
Yes. What is that?
Temperature should be kept constant.
Correct. That is at temperature T1, we are assuming that IC is equal to IC1 and beta equal to beta 1. Okay.
Yes,
At temperature T2, we are assuming IC is equal to IC2 and beta equal to beta 2. That is, you have to find the difference in IC. Okay. Because see here, what is the equation we are having? Delta IC by delta beta. What is delta IC? It is change in collector current. What is delta beta? It is change in current gain. Change in current gain. Small change in current gain. So this we are able to find if we are considering 2 conditions. right? What are those two conditions? One is at temperature T1, assuming IC as IC1 and beta equal to beta 1, and at temperature T2, IC as IC2 and beta equal to beta 2, so that we get the equation in the form of IC2 minus IC1, okay? That will give us delta IC, okay? And then beta 2 minus beta 1, that will give us delta beta, correct? So to get the equation in this form, we are using these two conditions. Got the point? So let us substitute these conditions. IC is equal to IC1 and beta equal to beta 1, first condition. So that will be IC is equal to IC1, that is equal to beta is equal to beta 1. Just substitute in this equation. We get VCC minus VB into beta 1, that is VCC minus VB into beta 1, that divided by RC plus RE into beta 1 plus 1, RC plus RE into beta 1 plus 1 plus RB, it is plus RB. Similarly, substitute IC is equal to IC2 and beta equal to beta 2. We get IC is IC2, that is equal to VCC minus VB into beta 2. So it is VCC minus VB into beta 2. The whole divided by RC plus RE into beta 2 plus 1, RC plus RE into beta 2 plus 1 plus RB. So it is plus RB. We got the equation for IC1 and IC2. What is the next step? Next step is we have to divide these two equations. Okay, divide equation 8 by equation 7. If we divide equation 8 by equation 7, we get IC2 by IC1. This is equal to beta 2 into VCC minus VB divided by RB plus 1 plus beta 2 into RC plus RE. This is cross multiplied by, denominator will come to the numerator here if you are cross multiplying, that is RB into multiplied by RB plus 1 plus beta 1, this term, into RC plus RE. Then in the denominator this numerator will come, that is into beta 1 divided by, into beta 1 multiplied by VCC minus VBE. This is IC2 by IC1. Let us simplify this equation further. IC2 by IC1, this we get it as, here it is beta 2 VCC minus VBE into RB plus 1 plus beta 1. VCC minus VB and VCC minus VB gets cancelled here. VCC minus VB in the numerator, it is a product term, and VCC minus VB in the denominator is also the product term. So both of these will get cancelled. Then what we get? RB plus 1 plus beta 1 into RC plus RE into beta 2. It is RB plus 1 plus beta 1 into RC plus RE into beta 2 in the numerator, and in the denominator RB plus 1 plus beta 2 into RC plus RE into beta 1. RB plus 1 plus beta 2 into RC plus RE into beta 1. Take it as equation 9. Next step. What is the next step, students? You have to subtract 1 from both sides of the equation. Yes or no? You have to subtract 1 from both sides of this equation. So if you subtract 1 from both sides of the equation, what you get? IC2 by IC1 minus 1, that is equal to RB plus 1 plus beta 1 into RC plus RE, the whole divided by into beta 2, the divided by RB plus 1 plus beta 2 into RC plus RE into beta 1 minus 1. Okay. Now we have to simplify this LHS. Take IC1 as LCM. It will be IC2 minus IC1 by IC1. That is IC2 minus IC1 by IC1. It is IC1 here. IC1, that is equal to, so now this, what is the LCM here? RB plus 1 plus beta 2 into RC plus RE, the whole multiplied by beta 1. This is the LCM. This will come where? This will get multiplied with this 1. Correct? Because it is the LCM. So this will get multiplied with this 1. Then what we get? RB plus 1 plus beta 1 into RC plus RE into beta 2 minus of this 1 multiplied by this denominator. Denominator term is RB plus 1 plus beta 2 into RC plus RE, that multiplied by beta 1. So the whole divided by RB plus 1 plus beta 2 into RC plus RE into beta 1. RB plus 1 plus beta 2 into RC plus RE into beta 1. What is IC2 minus IC1? It is delta IC. Therefore, delta IC by IC1, this is equal to, just expand it, we get RB, multiplied this beta 2 inside, RB into beta 2 plus 1 plus beta 1 into beta 2 into RC plus RE minus, multiply this beta 1 inside, it will be minus RB into beta 1 minus of beta 1 into 1 plus beta 2 into RC plus RE. Okay. The whole divided by RB plus 1 plus beta 2 into RC plus RE, the whole multiplied by beta 1. Simplify further. This is RB beta 2 plus RC plus RE is there in this term, and RC plus RE is there in this term also. Take it a common factor. Therefore, RB beta 2 plus RC plus RE multiplied by what we get here inside term 1 plus beta 1, 1 plus beta 1 into b2. Here also there is 1 plus beta 1 beta 2. Okay, here also there is 1 plus beta 1 beta 2. Okay, so RC plus RE into 1 plus beta 1 beta 2 minus, we have still not taken common factor, minus RB beta 1 minus RC plus RE into 1 plus beta 2 beta 1. Okay, divided by RB plus 1 plus beta 2 into RC plus RE into beta 1. Now let us take common factor as RC plus RE. RB beta 2, that is RB beta 2. Okay, RB beta 2 minus RB beta 1. RB beta 2 minus RB beta 1 plus RC plus RE is common in this term and in this term. Let us take it as common factor, RC plus RE plus RC plus RE multiplied by what is the inside term, RC plus RE multiplied by beta 2 into 1 plus beta 1 beta 2. Okay, so again we are multiplying inside here, so it will be beta 2 plus beta 1 beta 2. Okay, this beta 2 into 1 plus beta 1, or you multiply it inside, what we get, beta 2 plus beta 1 beta 2. Yes or no? This is RC plus RE is common, take it outside. Inside what we get, 1 plus beta 1 into beta 2 minus of 1 plus beta 2 into beta 1. Then I am expanding this 1 plus beta 1 into beta 2 inside term. What we get, beta 2 into 1 is beta 2 plus beta 1 into beta 2 is plus beta 1 beta 2. That is what it is written here. That is RC plus RE into beta 2 plus beta 1 beta 2. Then inside this will be minus beta 1 into 1 plus beta 2. That will come out to minus beta 1 into 1 is minus beta 1. It is minus beta 1. Then minus beta 1 into beta 2 is minus beta 1 beta 2. The whole divided by RB plus 1 plus beta 2 into RC plus RE, the whole multiplied by beta 1. Then what will gets cancelled here? Any terms gets cancelled here. This will be RB is common here. Take it out common, that multiplied by beta 2 minus beta 1 plus RC plus RE. Beta 1 beta 2 minus beta 1 beta 2 gets cancelled, plus beta 1 beta 2 minus beta 1 beta 2 gets cancelled. So you get simply inside term as beta 2 minus beta 1, beta 2 minus beta 1. This divided by RB plus 1 plus beta 2 into RC plus RE into beta 1. That is RB into beta 2 minus beta 1 plus RC plus RE into beta 2 minus beta 1. That divided by RB plus 1 plus beta 2 into RC plus RE into beta 1. Therefore, this is delta IC by IC1. LHS is what? Delta IC by IC1. Yes or no? Delta IC by IC1, we are getting this RHS equation. This delta IC by IC1 is equal to RB, beta 2 minus beta 1 is common, take it outside. Therefore, we get beta 2 minus beta 1 multiplied by RB plus RC plus RE. It is there in this term also, in the second term also, beta 2 minus beta 1. Take it common, we get beta 2 minus beta 1 multiplied by RB plus RC plus RE. That divided by RB plus 1 plus beta 2 into RC plus RE, the whole multiplied by beta 1. The whole multiplied by beta 1. Now we want the equation in the form of delta IC by delta beta. Right? Delta IC by delta beta is S of beta. So this beta 2 minus beta 1 is small change in beta, small change in current gain, that is nothing but delta beta. Beta 2 minus beta 1 is small change in current gain, that is delta beta. Therefore, delta IC by, if you take this delta beta to the LHS, it will come to the denominator, that is delta IC by delta beta is equal to this IC1. If you take it to the RHS, it will come to the numerator. Therefore, delta IC by delta beta is equal to IC1 multiplied by RB plus RC plus RE, that divided by beta 1 into RB plus 1 plus beta 2 into RC plus RE. Okay, this is the equation for S of beta for the collector feedback bias circuit. Okay, other names for collector feedback circuit is, that is DC bias with voltage feedback, or it is also called as collector to base bias circuit. Okay, these are the various names. So in examination, while asking, they may either ask as using the term collector feedback bias circuit, or the question may be using the term collector to base bias circuit, or DC bias with voltage feedback. All are one and the same. So that's all. That is a stability factor S of beta here. So any doubts here, students, in this derivation S of beta? Any doubts here in this derivation of S of beta? Understood this S of beta here? Steps remains the same. That's what I told. Steps remains the same. Okay, just the basic equation the input loop equation that will be different for the different biasing circuits, right? And based on that, applying the required steps, you will get the final equation for S of beta. Okay. Any doubts here? Abhay? Understood? Abhay? Is this derivation understood, Abhay? Adarsh? Adarsh? Kirti? Kirti? Understood? Prajwal Gowda? Prajwal Gowda? Is this derivation understood? Ratan? Ratan? Birje? Understood? Sadashiv? Sadashiv? Sai Prakash?
Yes, sir.
Understood derivation?
Yes, sir.
Is it clear how, what are the steps, how to do it?
Yes, sir. Yes.
Understood?
Ah,
Okay. Samir Ahmed? Samir Ahmed?
Yes, sir.
Is it clear derivation?
Yes, sir. Once more I will practice.
You want me to explain once again?
No, sir. I will practice, sir, once more.
Okay, just practice it. If you have any difficulty, you can ask me anytime. Okay,
Okay, sir.
fine. Sania, is it understood?
Yes, sir.
Clear of the derivation? How to find out S of beta?
Yes, sir.
Okay. Sanket? Sanket?
Yes, sir.
Understood?
Yes, sir.
Okay, fine. Shiraj? Shiraj? Mujawar?
Yes,
Shiraj?
sir.
Understood derivation?
Yes, sir. I will try once.
Yes, please try. If you have any difficulties, you can ask me anytime, right?
Okay, sir.
Okay. So let us move on to the just introduction I will give. Transistor switching networks. Okay. Transistor can be used as a switch or as an inverter. Okay. If we are operating the transistor in the cutoff and saturation regions, right, then we can make the transistor to work as a switch and also as an inverter. Okay. So let us see how the transistor works as a switch or as an inverter. Now, if you are applying the input voltage here, this is the transistor inverter circuit or the transistor as a switch circuit. We are connecting the collector resistance, and to the input side, we are connecting the base resistance. We are taking the output from the collector terminal. We are taking the output from the collector terminal. Okay, right? This is the basic circuit. What we have for the transistor as a switch or transistor as an inverter. Transistor, you know what is the meaning of switch. Okay, when the switch closes, it conducts. Right, you get a high voltage on it, or you get the current flowing through it. Right, the switch is open, then no current flows through it. No current flows through the circuit in an open circuit. Is it not? That is the meaning of closed switch and the open switch. So similarly, this transistor works also as a switch, that is a closed switch or an open switch, and it also works as an inverter. Meaning of inverter is it is working like a NOT gate. You have studied NOT gate in your basic electronics in your first year level, is it not? So it acts like a inverter or a NOT gate. That is, if we apply 1 here, the output will be 0. If you are applying 0 here as input, the output will be 1. Okay, it is acting like an inverter or a NOT gate. Okay, meaning of inverter is if you are applying the input voltage high, the output voltage will be low. If you are applying the input voltage low, the output voltage will be high. This is the meaning of the inverter. Okay. Now let us apply high voltage here. V in equal to V. When we are applying the high voltage V in equal to V, then this transistor turns on because the base current flows here, IB current flows here through this transistor to ground, and hence the transistor will be in on state. Transistor will go into saturation and the transistor will be in on state. So when the transistor is in on state or when it goes into saturation, okay, then what will happen here? Because of this turning on of the transistor or going into saturation, this transistor will act like a short circuit. This transistor will act like a short circuit because it is in saturation condition. We know that in transistor, when it is in saturation condition, the collector to emitter terminal will be shorted. Correct? We have seen this in various of the biasing circuits that we have already studied till now. Correct? So the collector to emitter terminal is just like a short circuit that I have shown in the second figure here. Collector to emitter is a short circuit, so it acts like a closed switch now. The switch is closed. It is closed here. Okay, the switch is closed. Between these two ends, it is a closed switch. It is a closed path. Correct? So it is a closed path here. And as the VCC gets directly connected to ground. So when it is a closed switch, what is happening here? VCC, which is there, the supply voltage, that through the resistance, it is connected to ground. What it means here? When it is connected to ground, it is shorted to ground. Therefore, what will be the output voltage? Output voltage will be how much? Yes, anybody can tell me? What will be the output voltage when the output collector terminal is shorted to ground? Yes. What will be the output voltage? Yes, please. What will be the output voltage? 0 volts. Because this terminal is connected to ground now. Okay. So this terminal is connected to ground. Right? This collector terminal is connected to ground. It is taking a ground path. Therefore, the output voltage will become equal to 0 volts. Output voltage will become equal to 0 volts. What input we had applied? V in is equal to V. We had applied high voltage or some voltage. Okay, at the input terminal. And what output voltage we are getting? We are getting 0 volts. So this is acting like an inverter, or it is acting like a closed switch. It is acting like a closed switch. When we are applying high input voltage, the transistor is in saturation condition. And transistor is in saturation condition, it is a short circuit or a closed switch, and the output will be equal to 0 volts, which is nothing but acting like an inverter. Okay, so it is acting like a switch and also as an inverter. Then let us see what will happen if V in is 0. If the input voltage is 0, how the transistor will behave. So if V in equal to 0 volts, what will happen? There is no current flowing through this base resistance. It is 0 volts. 0 volts means no current. So slight leakage current will be flowing. That is leakage current here. So because of this, the transistor will be in off state. Okay, it is in cutoff state. For the applying of high voltage to the base terminal, transistor will be in saturation condition. Okay, when we are applying low voltage or 0 volts to the base terminal of the transistor, then the transistor will go into cutoff state. Transistor in cutoff state means no current, or the collector current is 0. Collector current is 0. Transistor in saturation condition means we get the output voltage 0 for saturation condition. Transition cutoff condition means we get the output current as 0. The switch will be open here. Okay, because it's an open circuit. It is in cutoff condition means it is an open circuit. Okay, where we get infinite resistance. Because of the infinite resistance, it is open circuit. We'll be deriving the equations in the next class, where you'll be seeing how it is open circuit because of the infinite resistance. Okay, so as it is infinite resistance here, it is open circuit and the switch is in open circuit here condition. Therefore, it is an off switch. The switch is in off state. Previous one, when the input voltage was high, it is in on state. Switch is in on state. It is a closed switch. When input voltage is 0 volts, the switch is in off state, or there is no current flowing from between the two ends of the switch. So because of this, what will happen here? Whatever this VCC is there, that gets connected to this output terminal. Therefore, the output voltage will be equal to how much? Output voltage will be equal to VCC. Output voltage will be equal to VCC because this VCC will get connected to this output terminal or to the collector terminal. What input voltage we had applied here? Input voltage was 0 volts. But what output voltage we are getting here? Output voltage is equal to VCC. Right? That is, when the input voltage is high, transistor is in on state, output voltage will be 0 volts, switch is closed. Okay. Next condition, when V in equal to 0 volts, transistor is in off state, output voltage is equal to high, output voltage is high, and the switch is in off state or open circuit condition. Okay. So like this is how, students, the transistor will be acting like an inverter and also as a switch. So this is that what is called as transistor switching networks. Okay, that means transistor can be used as a switch and also as an inverter. The next class I will be writing the equations for the analysis here. For the transistor as a switch and as an inverter, we will be seeing various equations for what will be the collector to emitter voltage. Okay, equation VC equation. What is the equation for the base current IB? What is the equation for the output voltage? Okay, those things we'll see in the next class. Okay. Any doubts here, students, on this topic, transistor switching networks? You understood here how the transistor works as a switch or as an inverter? Yes? You all understood here? Is it understood here, students? Sanket?
Yes, sir.
Understood this?
Sir.
Transistor as a switch and as an inverter.
Yes, sir.
Okay, fine. Any doubts here? Any problem in understanding? Sanket? Pratmesh? Pratmesh? Is it understood? Tejas? Tejas? Shraddha? Shraddha? Kirti? Kirti Patil? Is it understood here? This transistor as a switch? Ratan? Ratan? Birje? Understood? Ratan? Harsh Gowda? Janvi? Janvi? Rutik Chopde? Rutik? Rutik Chopde?
Yes, sir.
Is it understood, Rutik?
Yes, sir. Understood.
Okay. Any doubts, Rutik?
No doubt, sir.
Okay.
We will try in home, sir. Again.
Yes, please. Try to analyze it. Just try to
Okay,
understand
sir.
it. Okay, in the next class, I'll be writing the equations. Okay, we'll take up the equations of transistor switching networks, right? You just go through.
Yes,
Right?
sir.
If you have any difficulty, you can ask me in the next class. Okay, at the beginning of the next class. Okay, Rutik. Okay.
Yes, sir.
Okay, fine. So, any doubts here, students? Any questions? Any difficulties? Any problem in understanding? Yes, please. Any problem in understanding? Sanya? Sanya?
Yes, sir.
Any problem in understanding?
No, sir.
Clear, right?
Yes, sir.
Okay, you understood this topic, transistor as a switch.
Yes, sir.
Okay, fine. Okay, we will wind up the session here. Okay. I hope everybody are writing the assignments. So please cover up the questions which are dealt in the class. Okay, which all are not covered, I'll be providing the notes to you all. Okay, related questions. Okay, which are not solved. Okay, I'll be providing the by tomorrow. I'll provide you the notes on that. Okay, you'll just try to write what all questions are being dealt in the class, related questions, whatever are there on the topics of the syllabus which are covered. You just solve those questions and then can send me. Okay. Anything you want to ask here? Anything you want to me ask here? Okay. Then we'll stop the class here. We'll take up the next part of the transistor switching networks in our next class. Thank you.